My name is Rastislav Marko, and I've been doing robotics since my studies. Previously, I worked on some service robots all around the software primarily, and now I'm leading the development of a robotic platform called Artaban, who is here with us today. I'd like to show it to you a little bit, and then maybe in the end we can do some more walking, but I'll continue with the presentation. Steering him, please come in if he's ready. Okay, so he's coming. Steering him is Edo, so if he's a little slow or crashes somewhere, okay, it's Edo, it's not him. Edo was a bus driver before. But this is our Artaban. As you can see, Edo is steering him with a controller. It's similar to playing a video game in principle. The robot basically is holding some balance, so if I disturb him a little bit, he is basically reacting to my disturbances. And like I said, we'll show it to you a little bit more in the end. But before that, I'd like to ask you, like, how many of you have seen a robot like this, maybe a yellow one, online somewhere in a video? Can you raise your hands for me? Okay, so most of you, perfect. How many of you have seen such a robot dancing? Okay, so I expected it was more. And then the question is, how many of you have seen a robot like this doing something useful? Not that the dancing would not be useful, but something in a sense that somebody would really pay for the robot to be doing all day long. So can you raise your hands? Okay, so that's a lot as well, but I would still like to emphasize a little bit, okay, that basically the home of these machines is not really the dance floor, but a setting maybe similar to the one you see on the screen. So basically this would be an infrastructure, some place which is potentially inherently dangerous, be it some facility, electricity, a gas facility, or any other. And basically the companies we talk to, they have a basically big problem with this, because their people are really being in danger every time they go into this area, and they're basically sacrificing their health, which is a really good place for a robot like this to be deployed. And that's why this is, let's say, the primary place where you would see a robot like this in the ecosystem with the other robots that you see in the screen performing some everyday tasks. Second problem is the labor shortage. Even the people who are doing these tasks today are aging. And as you can imagine, young people like to do cool jobs and not really the dirty and tedious, like doing an inspection all day and checking some analog meters and so on. So labor shortage is yet another kind of reason for these machines to exist and deliver value. And the last but not least, if you imagine a big facility delivering power to a city or similar, outages or some breakdowns are very costly. So really removing the human factor, the human error, and replacing, let's say, these tasks with some reliable, let's say, technologies that are, computers, mobile computers, is of a real big advantage. This is not the only place where you could find such a robot. Of course, apart from the critical infrastructure, you can also look into public safety and construction, which are, let's say, the domains where these machines find applications. And there is naturally more. That is how we started as a company as well in 2021. So our founders back then identified this demand, and they decided they deliver a solution for these problems to solve. And they looked around and they said, okay, maybe we can do it a little nicer, a little more in style. And that's why our robot has the distinct head, the eyes, that it potentially can convey some information to the people around him. And really they wanted to be, the robot to be basically accepted and pleasure to work with also from the visuals. So that's why we have also a little more bio-inspired body of the robot, still keeping the stealthy kind of robotic look of the origami style. After that, in 2022, we have actually shown that it is possible, in principle, to build a robot from scratch, and in Slovakia. We have completed some projects with this prototype. Unfortunately now it's retired because we have learned a lot along the way. Unlike some of the yellow ones, we didn't have 30 years, to experiment with. We had to iterate quickly, and so that's where we're here today with the red one. with a prototype 2. Maybe you could also hear it's also on the end of the life cycle right now, and that's why we're very happy to be building the yellow one, which is the prototype 3. We should have it anytime soon, really, like within a few days or weeks. So that's something we're really looking for. And in fact, we are not building it very far away from here. We are very local. We are based in the Block D, so just a few meters away from here, at the Faculty of Electronic Engineering and Information Technology, just next to the National Robotic Center. Sorry. Where this picture is from as well. And that is no coincidence that we're based here. We actually enjoy and benefit from the environment here. Every year we have students completing bachelor and master thesis with us. And as you can imagine, it's not just the students, it's also the faculty members and the academia. So this is a really nice way how to connect the practice with the academia. And we're very happy about it, about this ongoing collaboration. So if you happen to be students or not, reach out. We'll be happy to hear from you. In this picture, there's a little more heads than we actually are in our company. And the reason for that is that there are some external partners we work with. Building such a machine is not trivial. And as a small company, really less than the heads you see, we cannot really afford to build it from ground up. So we collaborate. We do not, let's say, wind our coils for the motors. We do not roll our cells, like battery cells. We basically buy them. We integrate them. But what we actually do is the mechanical design. So whatever you see, let's say, from the outside, then we got that hardware produced by some external partners. What we do is the electronics. So integrations of all the sensors, all the motion control and so on, doing some custom boards and so on. The primary, let's say, thing we really devote the most time of in our internal team is the software. And somewhat naturally, you can distinguish in this machine between the hardware and the software. That's what I'd like to show you about in a little more detail in the following slides. Whereas, because of the scope of the talk and the entire OpenSlava, I'll be focusing more on the software. But starting with hardware, as you already have seen, the robot is really just a body with legs, right? So that's what we call the mechanics. And in principle, you have to build it somehow. So we have chosen the carbon fiber, aluminum, and some steel parts, really depending on what the requirement on the part is, whether it has to be light or super stiff. So that's a big topic. Mechanical engineers dealing with that. In order to move the leg, if you imagine it as one element, of which there are 4 on the robot, if you want to move it to an arbitrary position in space, then you need 3 at least actuators, so that's something that really moves the hardware. And of course, our robot is a little unique in this case, especially in the paws. So we have some more degrees of freedom, that means more actuators, that allows us for more dexterity and manipulability. And there are some other advantages in terms of kinematics, like what torque we have or what speed we can achieve with our robot. Now, this is basically electric robot, and most of the industry is electric. Maybe you remember the Atlas robot, right? Doing crazy stuff. This is something very popular. So that was hydraulic, but since very recently they actually have a successor, which is fully electric. And there's a reason for that. Electricity is just, cheaper in terms of producing the actuators. The maintenance is much simpler, and also the control is basically simpler and so cheaper. And that's why, like all the machines around you see are just electric. We could go on with hardware forever, and like I said, I'd like to focus more on software. And another reason being that if we just had a little better software, with this hardware we could achieve most of what we ever wanted, right? It's not 100% true, but it's very close to being true. Really, software is the thing that we have to crack in order to kind of enable these machines to do the stuff we really want them. And so going to the software, the software on a robot like this is really broad, starting from the lowest level, communicating with encoders, up to highest level. And that's why I broke it down into like 3 categories, being perception, locomotion, and task planning. And starting with the perception, this is basically what the robot is like getting as an input from the world, right? Like the information stream. Naturally, the robot is equipped with encoders, so he knows where his legs are. So that's the first modality that the robot is perceiving. Second, similar to our inner ear, he has some inertial measurement unit in it. So he kind of has an idea of the balance. And you can already do something with this. So if you like blindfold it and try to walk, I mean, you can do something, right? But as you can imagine today, there is much better you can do. And that why is the robot equipped with an array of cameras all around, which are depth cameras. So with this, the robot can actually perceive the surroundings around him and kind of can feel where he is. With that, he can also localize itself. So in a picture, you see a point cloud that the robot has collected from the cameras, and the turquoise color is depicting the path that the robot has taken as he was traversing this terrain. So far, this has been on the, let's say, the onboard side. So that means all the, let's say, sensors and perception that is required for the operation. And then naturally, what comes onto his back is a sensor that is application specific. I'll come back to that later, but basically you can mount it and equip it with an arbitrary additional sensor. So once the robot sees, then it's time to act, so to do something in the world. And I'll start with an example, like you see in a picture, a little older robot, a hopping robot. I don't know if you can imagine what the robot does, but basically it's just a cage, metal cage with some actuators and with one telescopic arm that is pushing away, right? So what the robot can do is basically push its weight away. And back in the day, the control systems were very constrained in terms of computation. So the engineers who wanted to control such machines had to come up with some simplifications that would really allow, represent the entire complexity of the machine into something very simple that can be actually controlling the stuff. And in this case, you can imagine that the cage above is really just a potato, let's say, with some weight, right? And you could imagine a vector of force, basically pushing the potato up and down, right? So that's kind of a simplification you can make around it, which allowed the engineer to actually control a robot and make the hopping motion possible. Now, quadrupeds are in principle not much different, right? Instead of one telescopic hand or leg, you have as many as their legs in contact with the ground. So if you're on two legs, then you have two forces that are pushing you away. And also the potato analogy is not too bad to achieve some basic locomotion. So on the other side, you see the robot, represented as a simplified case. And if you think about it schematically, then in the bottom, you begin with the robot itself. Then a human brain has to, come up with a model, a potato or something else, more elaborate, and formalize it as some mathematical model, which you feed then into some optimizer, mathematical optimizers, whatever, linear, quadratic, there is plenty of them. And that makes the loop, which goes then back into the robot. So the optimizer can actually consume the robot model, consume the command from the robot, and basically spit out the forces you need to in order for the robot not to fall over, right? So this is what we today call classical locomotion. And it's still very vivid. It's still ongoing. Like I said before, also the Atlas robot has achieved whatever he has achieved based on techniques similar to this one. Of course, it was not a potato, but some more elaborate. If you want to see it in action, this is our Artaban in simulation. And you see basically all I was talking about. You see the forces. You see the plan, that's the green part, which comes into, right? And you can basically generate motion like this. I cannot display the forces on that one, so that's why I used the simulation. Now, one thing I didn't talk about is how you actually choose, where to put your feet. We humans have it simple. We have 2 feet, right? So you put one in front, then the other, and then repeat. Not much, of a difference through any motion we do. But as you can imagine with quadrupeds, it gets a little more complicated. And indeed, at least the biology, got very creative, as you can see in the scheme. So you have, horses and dogs and doing all kind of crazy patterns. So which one do you choose for your robot, right? That's a question. And once I was on a walk and I saw an older man with an even older dog walking upstairs, and that's when I was, this is the right moment to uncover. And of course, the dog was very old and was doing the cross pattern that you see almost on any quadruped these days. So basically changing the legs like this. And that's something that you probably want to do if you want to save energy and save your hardware. It is getting better, especially with some dexterous, crazy maneuvers, but that's what you'll see most of your robots doing. Now, there's been a lot of achievement, but of course, these techniques, the classical locomotion, come with some disadvantages, and there are like 4 black boxes or 4 blacks in this figure, and there are actually 4 problems with the approach. Starting with the human, I don't have to explain, humans are not perfect, right? Writing equations is difficult. And if you even manage to kind of write all your equations right, how would you describe something like this, which is mud? How do you write a contact model of this? And you want your robot to do backflip to really push the right way. It can get really tricky with the equations in the model. Going next to the optimization part, even if you had a model of this crazy stuff, then you wouldn't be able to run it online on the robot, because that's what is really happening on the robot. He has to recompute it like several hundred times a second, all over again, not to fall over, right? So there are some shortcomings. Of course, the robots break all the time. That's the 4th problem. But they break, like with any technique. So that doesn't really matter. So yeah, the question is, can we do better? Can we somehow dramatically not just improve, but change the approach and overcome all these limitations? And you guessed it, AI, right? It's everywhere. There's not a single domain where AI would not be present, and that's the same with robotics. So let's have a look at the pipeline of, let's say, AI approach to locomotion. It starts with the same thing. You take the robot, but instead of writing some elaborate equations, you just take it, throw it into a simulator, right? And then you define something you would like your robot to do. So please do not fall. That means like, I want the height to be constant. Let's say you give it some command, like go forward, right? And if you use, an optimizer over this simulation, some reinforcement learning like PPO or whatever, you have a high chance that basically what comes out is a neural network, which is relatively simple in comparison to, I don't know, LLMs and so on, and can do the control of the robot, right? So instead of the loop you see above, kind of incorporating the model and like lengthy optimization each time step, at the end you end up with some small, tiny thing that can run inference really quickly and follows your commands. Now there are some advantages like beyond the inference time of this, and that is mainly the generality of this approach. But if you only took the height and command, you could end up with something like this, which is in the picture, right? So the robot, his hip is relatively constant, check, and the command is, satisfied. He's going in some direction that the controller wanted, right? So maybe this is not really what you want. Of course, I just want to illustrate that it's not, simple, but with some clever tricks and some patience, you can actually achieve something that, is a little more pleasant also for the joints of the robot. And like I mentioned before, the generality of this is really the advantage, because you do not have to really include all the mud in your simulation and all the stuff. You just vary some parameters like slippage of, friction of the environment and so on, and the robot really can transfer to the real world much better than with the conventional approaches. Good, so now the robot can walk either way and see. Now it's time to make it useful in some way, and that's the job of the task planning, and that means like what to do when, right? Naturally, the robot is autonomous to the degree that it can go charging when it's necessary, or can avoid some obstacles, but still is the person, the human, who wants to be in control. And that's why we have this Panza platform, which is the place where you kind of define the missions or the tasks for the robot. So here you can basically define, okay, please, robot, go this path along the way, stop there, and do your job accordingly. if you have a fleet of robots, like is depicted in the figure, you can kind of have an overview of what's going on. If there are any failures, any alerts, this is the place where all the information comes in for you as an operator, right? So alerts, the data, all the stuff that the robot has collected, and so on. If you have a fleet of robots, naturally, then you can also individually have a look at how the robot is doing. So you can do some basic kind of status checking if everything is fine, all the equipment is working. You can peek into the camera streams which are running on the robot. And of course, in case of some unexpected situation, you can just take control like Edo did just before and steer it manually for whatever reason you wish. Yeah, so this is how you keep the robot busy. And the question is now, like, how do we keep our robots busy? So apart from a lot of development, since we're a young company, we have some ongoing projects and pilots where we did equip the robot with some sensors that I promised before. And one of those could be some gas detection, so we have some CO2 sensors. We also have a cool little thermal camera, so basically we have enabled the robot to kind of detect any anomalies that could happen in an infrastructure like you have seen before, measure some, I don't know, dangerous levels of gas that are not allowed and so on. And also we have a color camera, right? That sounds a little boring, but with today's AI, you can do magic. And with this color camera, which is really cool, zooming and all stuff, we really can do a lot. For example, we can detect some gauges, which are like analog meters showing, I don't know, like oil or whatever in the infrastructure, which is not digitized. So part of the infrastructure, naturally, you have connected to a cable, but many times the infrastructure is old and you cannot really afford to put sensors everywhere. So that's where these robots are going and really collecting the vital information in the dangerous environment instead of the humans. And you can do more. We've been doing some, like helmet detection, basically occupational safety and so on. You can do a lot with the cameras these days. So that's what we all do on top of the platform. That's, let's say, the present. But since this block is also called the future, emerging future, let's look ahead a little bit and then ask, like, what is next for these robots? And the very first and natural thing is to go really beyond sensing. So beyond being just a mobile sensor that is collecting stuff, and that is doing manipulation. I'm sure you have seen already some robots with an arm, but in the industry, companies are really struggling to do some basic bin picking these days reliably. It's not a solved topic at all, and especially in the real world, when you come out of some, constrained conditions, if you just wanted to, maybe grasp this glass, which could be empty or full, it's slippery, and hand it over to a human successfully. This is not solved. This has to be worked on, and this is something that will be a real enabler for these kind of robotic platforms, because it adds naturally a lot of value beyond just perceiving, manipulating the world. There is a lot of work, again, AI related as well. You have all the LLMs all around, and there are some robotics transformers in the game as well, where many labs have joined the forces to basically build something that is as generic and can morph to any topology of arm. So this is a big topic. It's very exciting, and that's going to be really cool to see in practice. Next, what is really being expected from these robots is generality and common sense. And I'll again reuse the figure from before. On the left, before maybe you remember, there was this height and command, right? But if you imagine that you would like your robot to, I don't know, fold t-shirts or do something more elaborate with the arm, then it might be a little tricky to write some, small rewards that you would like your robot to do in order to achieve the task. So these days, a common approach is really doing stuff from demonstrations. So on the left, you see a database of some motions. So in terms of humanoids, it's really simple because the human basically takes and teleoperates the robot, does what it needs to, ironing the t-shirt, folding the t-shirt, and then the optimizer takes that database of stuff and basically makes it work with the robot hardware to repeat that and with the same level of generality to kind of transfer to other domains. So that concerns the generality. And on the other side is the common sense. And that is yet another funny topic. Maybe you've heard about the robots which are patrolling some cities and then fell into a fountain or something. Or there were some pizza delivery robots which got stuck in some crossroad and caused traffic jam. So this is yet another thing that is missing really for these robots to have them amongst us, like you see in the picture. And that is the part of the figure on the right. And in case you're wondering what that cube is, I asked ChatGPT to draw an icon of a foundation model. So now you know, that's it. That's how it looks. And that's really, one cool thing about these LLMs, that you don't really have to change the way you control the robot. You don't have to start from scratch. You can really plug it into the, let's say, existing libraries of kind of motion primitives and so on. And you can just put an LLM on top of it and replace, let's say, the rigid human kind of mission planning with this thing that really has some common sense. So I'm sure you have seen already some demos of those multimodal models which are really taking some scene and extracting some high-level semantic knowledge about it. So seeing a room with different kind of shapes and objects. So this is what is really coming, basically placing some LLMs on top of the robotic technology and enabling them to really handle situations that may be tricky for them. For us, it's common sense, but yeah, really bringing the common sense to the robots. Yeah, and that's in principle what we are trying to build. This is the future we are envisioning, and we are very excited about for the future. I hope you're too. And yeah, if you are interested in this technology, like I said, let's say drop us a line, get in touch, and if not, then just enjoy OpenSlav and other topics. Thank you very much. Great, so shall we start with the questions? Perfect, okay. Have you considered the leg or more specific feet design that might have problems outside of hard surfaces, sand, mud, and water? Or can you somehow customize the robot to operate also on such surfaces? Thanks. Yeah, so like I said, in principle, the hardware is ready. It's really just what's going on in the brain of the robot, right? So what the controls is. And like I said, with those machine learning techniques, you can really achieve high robustness, even in those conditions that were just asked. So, of course, you can do some changes to the hardware, but it's much simpler, easier in terms of iteration time to really adapt the controls. And there are techniques, definitely, like I mentioned, to tackle these different conditions. So you have them climbing really rocky kind of terrains, muddy stuff. Yeah, it's ongoing. The next question. So what is the maximum number of sensors that can be customized on a robot? Is there any restriction? Yes, so I would say there are two restrictions. First is the weight. So, the robot cannot really carry a balloon of 2 tons. So weight would be the first one. We can carry up to like 10 kilos, let's say. And the second would be the space, right? Because different sensors may require different fields of view, so you have to arrange it in some way that you can really, make every sensor see what it needs to see. So these would be the two restrictions. How long does it run on a single charge? Do you autodock for charging? Yes. So does it run on a single charge? We are looking at some 2-3 hours, of course, depending again on the terrain. And regarding the autodocking, in the next version that we're very happy to have in a very short time, we'll also have inductive charging. So basically, you don't have to plug the cable into the back like you had to with this one. But the robot really just finds the docking station, sits down, and in a matter of few minutes or hours, it is charged. So yeah, working on that. Okay, I think I answered the first one. One thing that humans distinguish from animals is hand. Have you thought to combine Artaban with the mechanical hand? I assume that question was asked before I showed the pictures. Of course, so we already have a plan. We have the arm selected. We are, happy to dive into it as soon as we have a little more time on this topic as well. Yeah, so definitely ongoing. What is maximal speed and torque? Okay, so torque, in principle, could be different for every actuator, but let's say it could be around like 80 Newton meters per joint or like per actuator. And in terms of speed, this is again subject to the software. We could drive it faster, but then it gets tired quickly, so we have to slow down so that it doesn't overheat. But we're looking at some speed that is like close to human walking speed, so that's like 1.5 meters per second approximately, which is, by the way, perfectly sufficient for most of the customers. Like the customers normally don't want to do backflips at their facility, right? And don't want to like jump. They just want to do the job. And if it takes like a few minutes longer, that's perfectly fine. That's why also this design is not really meant, is not designed to do jumps and stuff. You have smaller robots for that. We are really aiming at robustness and basically carrying some load. Yes. Do you 3D print prototypes? We 3D print a lot. We have a 3D printer that is running almost nonstop at our facility. But like this is some real stuff, I'd say. It's really carbon. We cannot print everything. Most of what we print is really the internals or some minor parts that are kind of gluing together what cannot be done in a proper way, right? So we do a lot of 3D printing, prototyping, but not really the robot itself. It's rather inside. Do you use virtual simulation before production, like NVIDIA Omniverse on Unreal? Indeed, we have a lot of simulation. You have seen 2 of them. And NVIDIA Omniverse, we use one tool from the Omniverse, which is Isaac Sim, which is basically a simulator within the Omniverse. And that's where a lot of the reinforcement learning training happens. This is like a norm today. I mean, it's the only one that really does the job. So we do definitely do stuff, and I'd say we run, I don't know, like 10 times more hours in the simulation before we actually test it on a robot. So yeah, that's something you cannot really avoid these days, I would say. What is the price of the robot? Okay, so this really depends, but maybe I'll help ourselves a little bit with the competition. Normally, these robots are not sold as a piece, but they are kind of leased for, let's say, a period of time, a year. And normally, the math behind is the robot can do some stuff, which normally a human does. So there is some conversion, like this robot would be equivalent to, let's say, because it can run, 24/7, it can do something like 1 to 2 equivalents of human labor, right? So in the West, you have it, I don't know, like 100K up, depending really on the task that the robot is doing. And that's where we're going to be as well. Yeah. What are the benefits of your product in comparison with the competitors? Do you cooperate with them? And if yes, in which areas? Yeah, so I'd start with the cooperation. I mean, it's a competition, not a cooperation in the first sense. And what are the advantages? So first, I try to illustrate that we really focus on the user experience. We put a lot of value at the Panza platform so that it's really easy, it's natural for the humans, so they don't have to kind of have some technical issues with it. And the design. That's the thing we really work on hard and want to follow. And then also there's some mechanical stuff that I mentioned before. We are more dexterous, so we have more degrees of freedom. The front and the rear legs are different. If you can notice, most of the robots have them same because it's like kind of simpler. And we do have some advantages also. If you look at animals, they never come with the same legs in the front and in the back because the motion just requires different. So that's yet another advantage, I'd say, from the technical point of view. Shall I go on? Okay. No offense, but the dog you've made currently looks more like a spider, okay? And the cute robot character from Paw Patrol, okay? My children are curious. Will there be some design changes in the future? So this is a very, cool topic. We even did some studies with some Finnish multinational whatever partner, where our dog actually came best in this kind of acceptability study and even in the design. So it's really, up to you what it resembles to you. You said robot dog somewhere? No, I was imagining in my head maybe. So even it's not a dog, right? It's like whatever you imagine it to be. So it's really up to you. We like it. We're proud of the design. There is like a big renowned Slovak design studio who's responsible for the origami kind of shapes. So yeah, I mean, we can do more, but this is what we're happy with for the moment at least. Yeah. And the Paw Patrol, I forgot what I should react to, but yeah. I have some glimpses in my head. Not too different, you're right. Yeah. No offense. Okay, that was it. Cute robot. Okay, so it's not cute. Yeah, I'm sorry, up to you. What is the most promising, easy to implement use case that you can see apart from plain surveillance? I mean, you know, like I said, at the moment, it really is a mobile sensor. So you put something on it and you take information in, you process it to some, you know, abstract stuff that is, you know, easy for the human to kind of process. And that's why this is really the easiest kind of use case. I don't know how I would answer this question in a different way. Plain surveillance, so there are many aspects. So for example, we were talking with some security company. It's not going to be just surveilling. My baby with the body is going to be kind of, you know, acting as a bodyguard or whatever. So there are many things you can imagine. We're happy to, you know, for the customers also to come to us to suggest some new cool stuff. But the majority of where really the value is, where the companies can afford this solution, is what I just mentioned in the presentation. So that will be the easiest and the most kind of useful and natural to follow. Can you recommend a free platform for simulating, I guess, a robot in the virtual environment? Yes, so we already mentioned one. That is the NVIDIA Isaac Sim. That would be one, and the Gazebo would be like another go-to for, I don't know, most of the people starting with robotics or in robotics. Yeah. What is the weight of the latest Artaban? So we haven't weighted it yet because we're still waiting for the legs. But it should be around 35 kilos without no payloads, about. And this one is very similar. What do you do with the old prototypes? Right, so how do you say, we're scavenging them? So we're taking all the parts that we can still reuse to the new ones. We're just leaving them there to remind us of the past times. It all evolves. It's not very much useful anymore because, like I said, we have learned a lot of lessons. So it's really just, you know, a piece to be there and remind us of the past times for the moment. I think the others do it this way as well. If you go to Boston, they have a really long array of all the old robots they have used in the past. Yeah, I think I did answer that. And in China, robots are used during the lockdown to announce quarantine measures for humans. Is it possible in the near future to use Artaban robot in emergency services to help rescue search for missing people after natural disasters? Indeed, and this is also like one of the pictures I've shown. Let's see, kind of helping on all the domains like public safety and disaster and so on. However, with a note, this is still a little bit difficult. There are ongoing kind of research papers exploring this direction, but still the technology is not as mature. Normally, where you see these robots, even the most advanced ones, they're usually operating in a constrained space, which they know beforehand, which they have a map of. And basically they operate there in a monotonic way. So they really perform the tedious tasks, the boring stuff, repeatedly all over again, collecting something on a regular basis. I'm not saying that we're not aiming at this. We're already in discussions with policemen and so on. We'd like to do stuff like that, but this is maybe that is still requesting at least a little bit of the common sense that is coming into this machine. So this is definitely on the roadmap, but maybe not as a first and easiest, like somebody already asked, applications. You mentioned that business plan is to lend robots. What is the fleet number you want to achieve in 2-3 years? Good. So I am the technical person, and I'm going to try my best to answer this question. So naturally we do have some plan of building let's say the pre-production model next year. And then go to the production model, which will really be, hopefully deployed on scale. And if you multiply the numbers, I don't know, we're looking at, let's say, I don't know, up to 8 units next year. After that, hopefully we get up to, I don't know, like 20 units, and then you do the math, and hopefully we're scaling like we're all expecting from the business slides, right? So yeah, that's about the numbers, I guess. Good. Thank you for the questions. And we promise someone walking, we can still try to stand it up and show it to you. And like I said, this is approaching the life cycle now. So you can hear it, the falling of pieces. But yeah, thank you again.